Hi everybody, welcome back. What we're doing here today is we're starting a new chapter. That's chapter 28 of the textbook, and the topic here is sources of magnetic fields. To recap what we've done up until this point, as far as our magnetism discussion is concerned, we've talked about the effect that magnetic fields can have on moving charges, and also the effect that magnetic fields can have on wires that carry a current through them. So in terms of the force and the torque that it feels in a magnetic field. But up until this point, we haven't talked a whole lot about where magnetic fields come from in the first place. So what is it that causes a magnetic field? How can we calculate a magnetic field given we know something about the source of it? So that's really the focus here. Now, the format of the lectures are changing a little bit. I no longer have access to campus to film in the lecture room there. So instead what I'll be doing is filming from home. But I'm going to try to keep this as close to the format that we had before as possible. We're going to go through the slides, and then when we have things to work out like problems, derivations, and so on, we're going to do that on the board. Okay? So let's get into the new chapter. So the first thing we'll talk about is the magnetic field produced by a long straight wire. It turns out this is pretty much the simplest magnetic field you can see, is if you have a really long wire that carries some kind of current through it. The magnetic field it produces is relatively straightforward, so we'll start there and see what we get. So the magnetic field from a long straight wire is something that we can sort of break into two parts. Magnetic fields are vector quantities, so we want to get a grasp on the direction of the magnetic field, as well as the magnitude or the strength of the magnetic field. And these results that I'm going to quote to you here are experimentally true. So the reason we know these things is just from experiment. And let's start with the direction. So the direction of a magnetic field is going to be found by the right-hand rule. And if you look at the diagram here, what's labeled B is a series of loops that form circles going around the wire. Okay, so actually for a long straight wire that carries a current, the magnetic field lines form loops going around the wire, as you see in the diagram. Now, to get a sense of exactly how that works, the right-hand rule is useful. You can take your right hand and you point your thumb of your right hand in the direction of the current, and then the fingers of your right hand will be curling in the direction of that magnetic field. Okay, so again, it's forming these circular loops around the wire. The magnitude of the magnetic field, how strong it is, it depends on how far away from the wire you are. So if we take a look at the diagram, there's a point labeled P. That point is a distance r away from the wire. So the magnetic field strength, therefore, is given by mu naught times I divided by 2 pi r. And so that's what we use to calculate the strength of the magnetic field. It's inversely proportional to r, so that means as we get further away, as r increases, the strength of the magnetic field goes down, as you'd expect, but it also depends on the current, which is I. There's a constant in this equation here, which is mu naught, and this is a new constant that we need to discuss for a little bit. This is called the permeability of free space. It's a constant of nature, kind of like epsilon naught for electric fields, and it's given by 4 pi times 10 to the minus 7. The units are Tesla times meters over amperes. Okay, so that's just a new constant associated with magnetic field strengths that we're going to see from here on out. Okay, so let's do a conceptual question here so we can sort of work with these ideas we just presented. In this example, we have 4 wires which are carrying equal currents arranged in a square as shown below. Find the direction of the total magnetic field at the center of the square. So that's labeled point P. We're going to use the right-hand rule for this. So let's take a look. Wire number 1, which is on the upper left corner, is carrying a current going into the page. So imagine the wire itself extends into the page, and it's just a really, really long wire. Wire number 2 on the upper right, that's also going into the page with the current. And then 3 and 4, which are on the bottom, those are carrying currents going out of the page. So I want you to think about point P. What does the total magnetic field there look like just not in terms of a number, but in terms of, is it going up? Is it going down? Is it going to the left? Is it going to the right? Or is it 0 because everything cancels out? So take a minute to try to work this out. Pause the video, and then we'll go over it. All right, so let's work out this example. So what we're trying to figure out is, what is the total magnetic field due to these 4 different wires at this point P, which is right in the center? So let's take a look at wire number 1, which is up here. The right-hand rule says we take our thumb on our right hand and we put that in the direction of the current. So this current is going into the page, okay? Then the fingers of your right hand are going to be curling in the direction of the magnetic field. Okay, so the magnetic field here, due to wire number 1, is forming circular loops around the wire. Let me just kind of draw that real quick. Okay, we've got circular loops around wire number 1, but the direction at this point is down and to the left. So there's B1. Okay. Now, if we do wire number 2, it's the same idea. Okay, I put my thumb into the page in the direction of the current, and my fingers are curling in the direction of my B field. So we have circular loops going around wire number 2, and let's kind of draw that as well. But crucially, these are going clockwise. I should have drawn that before. So these B field lines are going clockwise. So at this point, that is up and to the left. There's B2. Okay, so the picture is going to get a little bit too cluttered, so I'm going to erase these B field lines I drew. And we'll go to wire number 3. So the idea is this one is out of the page. So I'm going to point my thumb in the direction of the current, which is out of the page. And now my fingers are curling around this wire counterclockwise. Okay, so the loops that these magnetic field lines form around wire number 3 is counterclockwise like this. So it looks like they're pointing up and to the left at point P. And then finally, if we do wire number 4, again, thumb is out of the page in the direction of current. We curl in the direction of the B field. B4 is pointing down and to the left like this. So the total B field at this point is just the sum of B1, B2, B3, and B4. We just add the magnetic fields together from the individual wires, and then we get the total. That's how it works. So these vectors, if we look at how they add, clearly the vertical components cancel, but we're left with something going to the left. So the total magnetic field in this situation is to the left. So this next one is a variation on the example we just saw. So we have 4 wires carrying equal currents arranged in a square pattern just like before. And just like before, what we're trying to do is find the direction of the total magnetic field at the center of the square. That's the one labeled point P. But this time, wire number 1, which is on the upper left, has a current going into the page. Wire number 2 now has a current going out of the page. Wire 3, that's at the bottom left, current is going out of the page. And then wire number 4, the current is going into the page. So once again, figure out if the total magnetic field at point P is going up, is it going down, is it going to the left, is it going to the right, or is it just 0? So pause the video, see if you can work this out, and then we'll go over it. All right, so this is just a variation on what we just did. We're simply changing around some of the current directions that you see. And as before, we're trying to figure out what the magnetic field looks like at point P due to all of these different wires. So we're going to start, as before, by looking at wire number 1. Current's going into the page, so I point my thumb that way. My fingers curl in the direction of the B field. So this hasn't changed. That's still down and to the left, like this. Now current number 2, which is up here, now that's coming out of the page. So if I take my thumb pointed out of the page, curl my fingers around, at point P, the B field is going to be moving down and to the right. So there's B2. Okay, wire number 3. Okay, our current is going out of the page once again. And so my thumb is going out of the page. I curl around like this at point P. And my B field is going up and to the left. So that hasn't changed from the previous example, right? 1 and 3 are the same. Now, with wire number 4, my thumb is going into the page because that's the direction of the current. Now my fingers curl around. So here, let's actually draw this one out. So B4, this magnetic field, again, it forms loops around the wire. Once we get to point P, it's going up and to the right. So I haven't drawn everything to scale, but hopefully you can see that all of these magnetic fields are equally strong because we have the same amount of current in each wire and I'm the same distance away from each wire at this point. That means the total magnetic field is going to be 0. They all cancel out. Okay, so the next thing I want to do is take this idea that a wire that carries a current produces a magnetic field. We just saw how that works. And combine that with an idea from chapter 27, which is when a wire is inside of a magnetic field, it can feel a force. So let's think about what that means. If we have 2 different wires that are parallel, as shown in the picture here, and they're each carrying a current, let's say I1 and I2, I1 is the current on the left and then I2 is the current on the right, we expect there to be some kind of force between these wires. What we're going to do here is figure out what is the math behind that. What is the math that tells us what the force between these 2 wires actually is? So in particular, we're going to look at the force that wire number 1 exerts on wire number 2. We'll start with that. Okay, so the starting point is wire number 1 is going to produce a magnetic field at the location of wire number 2. And that's going to exert a force on it. So let's first figure out, what does the magnetic field due to wire number 1 look like at the location of wire number 2? Okay, so you have to do the right hand rule here. Again, you're going to take your thumb, point it in the direction of the current I1, okay, and you're going to use your right hand. And then you'll see that your fingers are curling around, and at the location of wire number 2, you should see that it's going into the page. The magnetic field is going into the page. We're going to call that B1. Okay, so that's the magnetic field created by wire number 1, and it's B1. Now the magnitude of that magnetic field is something that we saw how to calculate. It's mu naught times the current, which is I1, divided by 2 pi times the distance to the wire, which in this case we're just calling that d. Okay, so it's mu naught times I1 over 2 pi d. That's how strong the magnetic field is at the location of wire number 2. Now, the next thing we do is we remember from back in chapter 27 that the force on wire number 2 is given by a cross product. The force on a wire that's in a magnetic field is given by IL cross B. So now we can sort of figure out what the force looks like. For the force, let's use the right-hand rule to work this out. So L is a vector that's going in the direction of the current. So the current here is I2. It's going straight up. Okay, and then if you curl the fingers of your right hand in the direction of the magnetic field, which is into the page, you're going to see that your thumb is going to the left. So again, fingers of your right hand in the direction of the current I2, then curl those fingers in the direction of the B field, which is going into the page, and now your thumb is going to the left. So the force that we're thinking about is to the left. So the way I write this is F12. That is the force that wire 1 exerts on wire 2. So it's going to the left. Now the magnitude, this is a cross product, IL cross B. So the magnitude of this force is going to be I2, that's how much current there is, times L2, that's the length of that second wire. Then we have B1, that's the magnetic field strength. And then we have sine of 90 degrees because 90 degrees is the angle between the current I2 and the magnetic field B1. Okay, now the next thing I'm going to do here is just plug in B1 and then set sine of 90 degrees to 1 because that's what that is. So when we plug in B1, we're going to have a number of things on top. We're going to have mu naught times I1 times I2 times L2. On the bottom, we're going to have 2 pi d. So again, that's just what we get by subbing in B1 and finding the force. Now, we also know by Newton's third law that wire number 2 is exerting a force on wire number 1, right? So if in the equation F12 we have some expression for the force that 1 exerts on 2, by Newton's third law, because we have equal and opposite forces, we have a force that 2 exerts on 1. So what's the takeaway of this? The two wires are actually attracting each other, okay? These two wires that are carrying a current that are parallel are attracting each other. So there's actually two ways this can go. Okay, the one we just worked out in a lot of detail on the previous slide is the case where you have parallel wires that are carrying currents in the same direction. So I1 and I2 are in the same direction. That's the picture on the left side. We get an attractive force between the wires. So the forces are going towards each other. They're attracting. In the other case, what we had is two parallel wires. This is the picture on the right side. What we have is two parallel wires with currents going in the opposite direction. Okay, so I1 is going in the opposite direction as I2. In that case, I'm not going to work this all out, but you can go through the same steps we did on the previous slide to show that the wires are going to repel each other. So now we have a repulsive force where these two forces, F12 and F21, are opposing each other. Okay, so the general expression for the force, regardless of whether it's attractive or repulsive for the force between these two wires, can be expressed as we found on the previous slide by this equation. Now typically, what we do is talk about the force per unit length. So just take our previous expression and divide out the length. That's force per unit length. What we get is mu naught times I1 times I2 divided by 2 pi d. That's what we get when we just divide out the length in our force equation that we derived previously. Okay, so now we know how to handle and calculate the force between two wires. So let's just get a little practice utilizing this equation, making sure we know what to do with it. In this question for the class, we have two parallel wires in an extension cord that are separated by 3 millimeters. Each wire has a length of 2 meters. One wire carries the current from a 32 volt DC power source to a light bulb, and the other wire carries the return current. Okay, so that's all shown below. The resistance of the light bulb is 4 ohms. What is the magnitude of the force between the wires? And as a follow-up, is this force attractive or repulsive? So pause the video, try to work this out, and then we'll go through it. Okay, so now we want to find the force between these two wires in an extension cord. And the first thing we should figure out is what is the actual current running through this wire. So for this, we're going to use Ohm's law. Okay, the voltage that we apply is equal to the current times the resistance. And if we're interested in finding the current, well, that's just voltage divided by resistance. In this case, our voltage was 32 volts, and our resistance was 4 ohms. Remember that an ohm is just a volt per amp. Okay, so that's really easy. The current is 8 amps. And that's actually the current in both of these wires because they're carrying the same exact current. One is just carrying it from the power source to the device. The other one is just carrying it back to the power source. So it's the same current either way. So we have these two parallel wires. One's carrying a current going to the right. Let's call that I1. The other is carrying a current going to the left. Let's call that I2, but here, we know I1 and I2 are the same thing. same current, it's 8 amps. Okay, so what kind of force is involved in this? Well, is it attractive or is it repulsive? We learned just a second ago that if the currents in these two parallel wires go in the same direction, they attract. Okay, if the currents are going in opposite directions, which is the case here, that implies that there is a repulsive force. So they're going to be repelled from each other. Okay, we should label the distance between them here. That's d. The length, let's call that L. And I think now we're ready to solve the problem. We found that the force per unit length is equal to mu naught times I1 times I2 divided by 2 pi d. And okay, if that's the force per unit length, what if we just want the force? Just put length over on the other side, like this. All right, so now we're ready to calculate. The force of repulsion between these two wires is equal to mu naught is 4 pi 10 to the minus 7, and the units are Tesla meters per amp. For I1 and I2, they're the same, 8 amps. And then for the length, what we have is 2 meters. Divide that by 2 pi times the distance. Now the distance here is 3 millimeters. So we've got 3.0 10 to the minus 3 meters. Okay, what does this work out to? You get about 8.53 times 10 to the minus 3 newtons, or if we round to 2 sig figs, about 8.5 10 to the minus 3 newtons. That's not much force. Okay, so in an extension cord where you have these two currents running in opposite directions, yeah, they do repel each other, but not by any kind of noticeable amount. It's a really tiny force. Okay, so here's another example where we are suspending a wire with a current. So here's what's going on in the picture. A long horizontal wire has a current I1 is equal to 80 amps running through it. So I1 is the wire on top, it's 80 amps. A second horizontal wire is placed at a distance 20 centimeters below it. This second wire has a mass per unit length of 0.12 grams per meter. What current should we run through the second one? What should I2 be in order for it to be suspended in the air? And in what direction should the current flow? Okay, so here's the idea. If this wire feels an attractive force towards wire number 1, pulling it up, that can counteract gravity, which is pulling it down, and it can just float there and be suspended in the air. This will only work if there's a very specific value of current running through it. So our job is to figure out what that current I2 has to be to balance out gravity with this magnetic attraction between the wires. Okay, so let's work this out. All right, so in this example, we're suspending a wire, that's wire number 2 down here, in the air by applying a magnetic force to it that counteracts gravity. Okay, so if we want this thing to float there, here's what we need. Okay, if we draw a free body diagram of this second wire, the one down here, there's going to be a force of gravity, Fg. There's also going to be a magnetic force, we'll call that Fb. And they need to cancel each other out in order for it to actually float there. So obviously the magnetic force has to go up, which means it's an attractive force. And if we have an attractive force, we need the current I2 to run in the same direction as the current I1. The only way you get an attractive force between these parallel wires is if the currents go in the same direction. So that's what we're going to have here. Currents going in the same direction, I2 is going to the right. So if the wire floats, okay, what we're going to have is these two forces, Fb and Fg, equal to each other in terms of their magnitude, but we already said they're going opposite directions. So what is the force of gravity? Well, that's just m times g, i.e. it's the mass of this wire times 9.8 meters per second squared. What's the other force? Well, Fb, that's just equal to, if we work it out, mu naught I1, I2 times L divided by 2 pi d. Okay, so we're going to put that equal to the force of gravity. So we're going to put that equal to m times g. All right, what am I trying to solve for? I'm trying to solve for I2. I want to know what that current in the second wire has to be to get this all to work out. So let's solve for I2. Okay, I2, that is equal to, first, we're going to take 2 pi d and multiply on both sides. So on top, I'm going to have 2 pi d times m times g. Okay, then I'm going to divide out mu naught times I times L, divide it from here. So I'm going to have mu naught times I should say I1 times L. There it is. Okay, the next thing I'm going to do before we plug the numbers in is sort of rewrite this slightly. On top, we have 2 pi. We have the distance between the wires. And I want to take m divided by L and just kind of put that as a single term, right? Because what we know is the mass per unit length of this wire. Then we have g, and then on the bottom we have mu naught times I1. Okay, now we'll put the numbers in. So on top we have 2 pi. Actually, let's go down here. I don't think I have enough room. On top we have 2 pi. The distance between the two wires, we found that to be 20 centimeters or 0.200 meters. The mass per unit length. So we had 0.12 grams per meter. We want this in kilograms. 0.12 10 to the minus 3 kilograms per meter. That's the mass per unit length of the wire. And then for G, we have 9.8 meters per second squared. Got to divide that by mu naught, which is 4 pi 10 to the minus 7 Tesla meters amps. That's the unit. And then I1, that was 80 amps. So what does this work out to? Well, it's 14.7, but we'll keep 2 sig figs amps, so about 15 amps. That's how much current you need to run through that second wire so that it floats there and is suspended. Okay, so before we move on to the next part, I do want to say a little bit about units here. So we have this new constant, mu naught. It's called the permeability of free space, and it usually appears whenever we're calculating a magnetic field. And if you notice, it has a pretty unique value. It's 4 pi times 10 to the minus 7 Tesla meter per amperes. Now, that's not a coincidence, right? It doesn't just happen to be 4 pi times 10 to the minus 7. It's actually defined to be that way. Okay, so we just fix the value at 4 pi times 10 to the minus 7. And once we do that, it defines what the other units are for us. So for instance, the ampere. How do we know what an ampere is? How do we define this unit in practice? Well, if we have 2 parallel wires that are separated by a meter, and the force per unit length between them is 2 times 10 to the minus 7 newtons per meter. So we saw earlier that, of course, if you have 2 parallel wires, they exert forces on each other. That's something we can measure. So if the force per unit length is exactly 2 times 10 to the minus 7 newtons per meter when the wires are separated by a meter, that defines the unit of an ampere. That's the current flowing through those 2 wires. And okay, so if we know what mu naught is, we have a way of defining the ampere. And then we have a way of defining the Coulomb, because an ampere is a Coulomb per second. And so then we can say a Coulomb is an ampere times a second. So if we have a definition for the ampere, and we know what the definition of a second is, that can give us the definition of a Coulomb. Now, this may all seem kind of strange. Why do we need to go into the lab and measure the force between two wires to know what an ampere is? Well, this is actually something that does very commonly happen in science. These are called operational definitions for our units. In other words, we have a definition of our unit which is given by some kind of procedure that we can do in the lab to get exactly, for instance, 1 ampere or 1 Coulomb or whatever the case may be. So anyway, that's a little note on the units. Now we'll move on to the next topic, which is Ampere's law. Okay, so Ampere's law in a nutshell is a way to calculate a magnetic field. So let's get into it. The idea behind Ampere's law is like this. If we have a magnetic field and we integrate over that magnetic field, so in particular, now I'm talking about a path integral, b dot dl. Now, if we do that integral, b dot dl, over a closed path, then I use this special integral symbol with a little circle around it. So integral over a closed path, b dot dl, is what we're talking about. Let's think about different ways this integral could go. So in the picture on the left side, here's what you're seeing. You're seeing the magnetic field produced by a very long wire that's carrying a current I. So the current is coming out of the page. So imagine in this case that the current or the wire is coming out of the page at you, and it's carrying a current in that direction, coming out of the page at you. Now, we know from the right-hand rule that if you take your thumb and you point it out of the page, you'll see that your fingers are curling counterclockwise. So all of the B field lines that I'm showing you here, the magnetic field lines shown in red, are going counterclockwise. They're forming loops around the current as we saw before. Okay, so then if you look at path 1 and path 2 that are shown here, there's a difference between them. So path number 1, it's a closed loop, and we can integrate the magnetic field around that path. But the loop itself, or the path itself, doesn't enclose any current, right? So that path number 1 doesn't contain the wire. It's completely outside of that, so it's enclosing no current. Now path number 2 that you see, it actually is enclosing the current, right? Because it's surrounding the wire. So there's a crucial difference between these two integrals, okay? If I do the integral of b dot dl for path 1, I'm going to get 0 every single time. As long as that path is enclosing no current, I'm getting 0 for my integral of b dot dl. For the other path, as it turns out, the one that is enclosing a current, I'm not going to get 0 for that integral. So really that sort of defines the idea behind Ampere's law, is if I take the integral over a closed path that encloses some current, I'm not going to get 0, and I'm going to actually get something that can help me calculate what the magnetic field is. So I'm going to sketch this out for you in a little bit more detail on the board in a second here. So let's go into that.
Okay, so I'd like to make a quick side note to sort of motivate Ampere's law, where it comes from, and why we should believe it's true. So in this picture, what I'm showing you is a current which is coming out of the page. So imagine we have a really long wire going this way out of the page. The current runs like this. We know which way the magnetic field goes. It forms a little loop like this around that current, and that magnetic field is labeled B right here. Okay? What I'm interested in is integrating over this magnetic field along a certain path. Okay, so in this case, my path is going to be a complete closed loop, and I'm going to construct it in 4 different pieces. Okay, so first, I'm going to go in a half circle like this. Then I'm going to go straight up, then in another half circle like this, and then back to where I started. So those are 1, 2, 3, and 4. Those are the different parts of my path. Now, the thing we should note about this path is that it encloses no current. So my path is made in such a way that I'm trying to get around the current and I'm not actually enclosing it. So if I want the total integral of b dot dl for this closed path, well, again, I can break it up into these 4 parts. I've got b dot dl 1, I've got b dot dl 2, got B dot DL3, and I've got B dot DL4. Okay, so we're going to think of it in those pieces. Now, immediately I can say that B dot DL for both paths 2 and 4 are both going to be 0. Why is that? Well, my B field lines, if I'm looking at path number 4, are going to the right, like this. But my path itself, my DL, is going up. So they're perpendicular. My B field and my DL are perpendicular to each other. And when you take the dot product of two things that are perpendicular, they're at 90 degrees, you always get 0. Okay, so for the reason for this is, again, that B and DL are perpendicular. Okay, so let's actually cross those out. For 2 and 4, we know we're just getting 0, so we can ignore those. That means we can concentrate our attention on paths 1 and 2. And again, we're going to just figure out what the integral of B dot DL for this magnetic field is for these two different paths. Okay, so let's take number 1, how about? Let's do B dot DL for path number 1. Okay, so what's going on here is my DL vector is pointing along the path that's going counterclockwise, as you can see here. But my B field is also going counterclockwise, so they're going in the same direction. That means I can take the magnitude of B, the magnitude of DL1, and then just cosine of 0 for the dot product, because they're going in the same direction. All right, well, cosine of 0 gives you 1. The next thing we can do is take B. Since all along this path, I'm staying the same distance away from the wire, okay? The B field has the same strength, it has the same magnitude all along this path, okay? It only increases or decreases in magnitude if we're going closer or further away from the wire as we travel along the path. But in this case, B is just the same strength everywhere along that path. So it's a constant. In other words, it can be pulled out of the integral. And now I have B, and then I have DL1. B is the strength of the magnetic field, and DL1 is, when I integrate it, the total length of that path that I labeled as 1. Well, it's half of a circle, so it's half of the circumference to give me that total distance. So I'll actually put that in first. We have not 2 times pi r, but just pi r, okay, because that's half a circumference. But then for the strength of the B field, we have a formula for this, so why don't we just use it? The strength of the B field is mu naught times I divided by 2 pi r. Okay? So pi's cancel, r's also cancel, and I'm left with just 1/2 times mu naught times I. Okay? And now let's do it for the last path, which is number 3 over here. All right, so the thing we need to notice about this path is the DL is going clockwise like this, but my B field lines are going exactly opposite to that, counterclockwise. Okay, so I have a DL vector and a B vector. They're not going the same way, they're going exactly in opposite directions in this case. So now what I have is B, DL 3, yeah? So the magnitude of B times the magnitude of DL3 comes cosine of 180, because these vectors now exactly oppose each other. Cosine of 180 is -1. Okay, B is constant over the path for the same reason as before. And then we have DL3. Okay, so this looks similar to what we had before, except we have a negative sign out front. So we have mu naught times I divided by 2 pi r. That's the strength of our magnetic field, negative sign out front. This is also a half circumference. If I take the total length along path 3, it's half a circumference, which is going to be pi times r. All right, so cancel out pi times r. Now I have minus 1/2 mu naught times I. All right, what's the takeaway point of this? If I do this integral over a path where we enclose no current, what we get is 0, okay? So I just showed that these two cancel out, and we're left with 0 for this total path integral, okay? That's the lesson. You enclose no current, you get no. Right, so now we're going to do a slight variation on the example we just saw, where before our path, it was not enclosing any current, but now our path is enclosing a current. And I want to keep things as similar to what we saw before as possible. So what I can do is, let's keep path 1, path 2, and path 4 exactly the same as what we had earlier. But now let's have path 3 going to the left like this, as opposed to going to the right over here, as it was previously shown. And now we can see that this dashed line representing our complete closed path is actually enclosing a current. So this is different because our path is now enclosing some kind of current. So the total integral of b dot dl over the path, just as before, we can break it into the 4 different parts. And just like before, path number 2, path number 4, that integral is going to come out to 0. The reason for that is because the path and the magnetic field are at a right angle. They're perpendicular to each other. So cross those out just like we did before. Path number 1, it hasn't changed. It's the same thing we had earlier. And that worked out to 1/2 mu naught times I for the integral b dot dl. So we're going to just use all of that stuff that's the same as before. The only thing that has changed is now b dot dl for path number 3 is different. So let's work out what's changed. We have a dot product of 2 vectors. As before, we can think of that as the magnitude of the first, the magnitude of the second, and then cosine of the angle between them. So notice how my B field is going counterclockwise, just like before. My path, number 3, is also going counterclockwise. In other words, they're going the same direction, the B field and my path. So the cosine of 0 is what we put for this dot product for 2 vectors that are parallel going the same way. Okay, cosine of 0, that's 1. B field, as before, is uniform. It's constant over the path. So we can pull that out. And now we have dl3 on the inside. Okay, it looks like we know how this goes because the magnitude of B is mu naught times I divided by 2 pi r. And the total distance that we travel going across path 3, well, that's just half of a circle. Pi r is the half of a circumference. Okay, so pi r cancels. This comes out to 1/2 times mu naught times I. So before, this came out negative, and then these two canceled, and then the whole integral came out to 0. Now it's coming out positive. So when we take the entire integral b dot dl for the closed path, when we do enclose a current, that's going to be, add these two together, well, you have a 1/2 times mu naught I plus 1/2 times mu naught I. You just get mu naught I. And really, this is Ampere's law. This is what it's all about. If you take the integral of b dot dl over a closed path, that equals mu naught times the current that you're enclosing with that path.
Okay, so we've got the basic idea behind Ampere's law, and now we can state exactly what it says and how we can use this. So Ampere's law gives you a mathematical relationship between B fields, which are magnetic fields, and the sources, which are electrical currents. And this law was discovered in the early 1800s by a French mathematician and physicist whose last name is Ampere. And here's what the law says. Okay, we have the integral of b dot dl over a closed path. that equals mu naught times I enclosed. Okay, so mu naught is that constant we saw earlier. It's called the permeability of free space. And I enclosed is just whatever current we're enclosing with our path. Okay? So this kind of looks similar to Gauss's law in a lot of ways because it gives us some kind of relationship between a field and the source of that field, and it's all expressed in terms of this integral. And also, like Gauss's law, there's a little sort of imaginary object that we draw on our diagram in order to use Ampere's law. And so this is called an Amperian loop. So to do b dot dl, to do that integral, you have to integrate over some kind of loop. And again, this is not necessarily anything that's real or that actually exists, but it's just something you construct in order to analyze what's going on in the problem. Okay, so here we have a conceptual example which deals with Ampere's law. If you look at the diagram below, you'll see that there are 6 wires, and the currents in these wires go into or out of the page. So imagine the wires themselves are really long, but they're perpendicular. They run perpendicular to the plane of the page that you're looking at. So some of them have currents going out of the page. Those are shown as a little circle with a dot in the center. That indicates a current going out of the page. The circle with the X in the center indicates a current going into the page. Okay, but in terms of the magnitude of these currents, they're all equal. What we're going to do is rank the 4 loops, A, B, C, and D, that you see, in terms of the integral over the magnetic field, that's b dot dl. So which one has the biggest integral for b dot dl? Which one of them has the smallest? Let's rank them in terms of that integral. So at this point, pause the video, see if you can work this out, and then we'll go through the solution. Okay, to get this one, what you need to think about first is how much current is each one of these paths enclosing. So what we're going to do is find the total current enclosed by each one of these paths. And we'll start with path A. That's the big one that's surrounding everything. Now path A surrounds all 6 of the wires, and 3 of those wires have a current that's coming out of the page, and then 3 of them have a current that's going into the page. So if I think about the total enclosed current, I would have to take 3I minus 3I, because again, the 3 currents going out of the page are in the opposite direction as the 3 currents going into the page, so they do cancel out when they go in opposite directions, and overall we get 0 enclosed current. For path B, if you look at path B, it encloses 2 wires that carry a current going out of the page, and it encloses 1 wire that carries a current going into the page. So the total enclosed current by path B would be 2I minus I, and then that just gives us I. All right, now we move on to path C. If you take a look at path C, you'll see that it is enclosing 2 wires, and both of them have a current that is going out of the page. So the total current enclosed with path C is just 2I. Finally, we'll move on to path D. You'll see that that one in the diagram is enclosing 2 wires. One of them is a current going out of the page, the other has a current going into the page. So as we saw earlier, those 2 cancel each other out and you just get 0. So why does this matter? Well, remember Ampere's law says that the integral b dot dl over a closed path is just equal to mu naught times I enclosed by the path. So if we know the enclosed current for all of these paths, and we know how to rank those, then we know how to rank b dot dl for all of these different paths. So which one has the biggest integral? Well, it's the one with the biggest enclosed current. That's path C. Which one is the next one? Well, that's path B. And then the last 2 are A and D. Okay, so the integral for C is the biggest, followed by B, then followed by A, which is also equal to D because they're both 0. Okay, so that's how we rank these in terms of b dot dl. Okay, the next thing to talk about is how we can start using Ampere's law to calculate a B field. Okay, so I know what the current in some kind of system looks like, and I want to use that to calculate the B field. Ampere's law gives me a way of doing that But there's a catch. Ampere's law is really only useful if we can exploit some kind of symmetry. So it's similar to Gauss's law in that sense. We can only use it when we have a certain symmetry that we can use. So if you think about why that is, remember Ampere's law says we integrate b dot dl over some path, and that equals mu naught times I enclosed. If my goal here is to solve for the B field, solve for B, I'm going to have to be able to pull it out of the integral if I'm going to solve for it. Okay, so only if your B field is really highly symmetric can you actually pull B out of the integral and solve for it. So there are 4 cases that we're going to look at. This is all we need to know for Ampere's law, these 4 types of symmetry. The first one is an infinite straight wire. Okay, now there are different variations on that, but basically the symmetry is you have a really long cylinder carrying some kind of current, and we can calculate the B field from that. The next one is a solenoid. So if you haven't seen a solenoid before, here's what it is. What you're seeing in this picture is a wire that's wrapped around a cylinder many, many, many times, and that creates a sort of magnetic field. We'll be able to calculate that type of magnetic field using Ampere's law as well. The next one is a toroid. So this is something that's shaped like a donut, and wrapped all around that donut is a bunch of turns of wire. Again, it's wrapped around the donut many, many, many times. That's really what a toroid is. And then lastly, an infinite current sheet. So imagine an infinitely large plane that just has some current flowing through it. That's the last case that we'll look at. So we should be able to use Ampere's law for these 4 types of symmetry. These are the ones we should concentrate on, these 4 examples. So why don't we start with Ampere's law applied to an infinitely long and thin wire. So here's what's going on with this infinitely long thin wire. The current in this picture is going straight up, and we know how to think about the magnetic field produced by this wire. We can use the right-hand rule. So what I want you to do at home is take the thumb of your right hand, point it up in the direction of the current, and you'll see that the fingers of your right hand now curl around the wire. So those B field lines that are curling around the wire just show you the direction that I'm talking about. Okay, so again, the B field lines are forming these closed loops around the wire. That's what it looks like. So when we use Ampere's law, we have to pick something called an Amperian loop. So this is a loop that we use to do the integral, but it's not, again, something that's real. It's just something that we sort of put on our diagram as a tool to help us solve the problem. So the Amperian loop that I'm choosing to use here is a circle of radius r centered on the wire. Now, how much current am I enclosing with that loop? Well, this is pretty easy. I'm enclosing the whole wire, so whatever current is going through the wire, that's what I'm enclosing with my path. So that part is pretty straightforward. Now let's do Ampere's law. Let's apply B dot dl is equal to mu naught times I enclosed. So B, that's the magnetic field vector. That's shown in red with these loops going around the wire. Now dl is a little bit of this Amperian loop. It's a little bit of distance along the path. And so my dl vector is shown right there. And here, let's do the integral B dot dl. Well, whenever I have a dot product, the way you think about this is it's the magnitude of the first vector, so the magnitude of B, times the magnitude of your second vector, that's the magnitude of dl, times the cosine of the angle between them. Now, there actually is no angle between B and dl. They're pointing in the exact same direction. So for that reason, we take the angle to be 0, and we'll have cosine of 0, which, if you remember, just gives you 1. Now, the magnitude of B is actually going to be constant or uniform all around this loop, because the magnitude of B only changes with distance. So if I'm getting further away from the wire or if I'm getting close to it, that will change the strength of the magnetic field. But as long as I'm staying the same distance away from the wire as I go around this Amperian loop, then B is uniform. It's just a constant. So I'm going to pull out that magnitude of B, and here's what happens next. I've got magnitude of B times the integral of dl all around this closed loop equals mu naught times I. That's what we have so far. So when I think about the integral over all my dl's, I'm adding up all those little distances around my Amperian loop. Really, that's just giving you the total distance around a circle, i.e. it's the circumference, 2 pi r. That's the total distance around my Amperian loop. So now what I have is magnitude of B times 2 pi r times mu naught times I. And so when we go ahead and solve for the magnitude of B, by dividing out 2 pi r, we get mu naught times I divided by 2 pi r. So this should look familiar. This is the very first thing we went through in the lecture. The strength of the magnetic field due to an infinitely long wire is equal to mu naught times I over 2 pi r. That's what we saw at the very start of the lecture. So we can get the same result using Ampere's law. Okay, so this will be the last thing we go through, and then we'll end the lecture here. So using that previous result, I have a question. What would the current flowing in a long straight wire have to be in order to produce a magnetic field with a strength of 1 Tesla at a distance of 1 meters? So the permeability of free space, that's mu naught, that value is given to you. You're going to need to know that constant to do the calculation. So we're just using the result from the previous slide that the magnetic field from a infinitely long straight wire is equal to mu naught times I over 2 pi r. So use this to answer the question. Pause the video, try to work it out, and then we'll go through it.
So in this example, what we're looking at is a wire that has a current running through it, and there's going to be a magnetic field produced by that wire. What we're trying to get is a sense of how much current would we have to actually run through the wire so that if we're a distance of 1 meter away, the magnetic field strength would be 1 Tesla. So this is the basic picture. There's the wire. Let's say the current is going up in the diagram. We're a distance r away from the wire here. And the right-hand rule tells us which direction our magnetic field is going in. So take the thumb of your right hand, point it up in the direction of the current, and now your fingers are curling around like this. Okay, so at this point, the magnetic field is going into the page. That's the direction your fingers would be curling in. If you do the right-hand rule, it's into the page. Well, actually, in this case, we don't care so much about the direction of the B field. We just care about the magnitude or the strength of the B field, and that's given by mu naught times I divided by 2 pi r if we have, a long straight wire like this. So what we'll do next is figure out what the current is, because that's what I care about. I want to know how much current needs to be running through this wire. So to solve for I, we have 2 pi r times magnitude B divided by mu naught. So the current, that's equal to 2 pi. Now r represents the distance away from the wire. Here, that's going to be 1 meter. Okay, then we have the magnitude of B, which we're saying is going to have to be 1 Tesla. That's what we're trying to get to. And mu naught is just this constant called the permeability of free space. And the value is 4 pi 10 to the minus 7. And the units happen to be Tesla times meters divided by amps. So check this out. Meters cancel, Tesla cancel, and then amperes go to the top. So we're going to get some kind of current in units of amps. We get some ridiculous amount of current here. It's 5.0, 10 to the 6 amps. Okay, 5 million amps of current. That's how much it's going to take just to get 1 Tesla of magnetic field strength if you're only a meter away from this wire. So really think about how that would go. If you tried to run 5 million amps of current through a wire, you would immediately vaporize it. You would just immediately destroy it because, of course, when you run current through a wire, It produces thermal energy. This much current is just going to completely destroy the wire in an instant. You would never be able to run this much current through a wire. So how is it that in reality we can produce magnetic fields with the strength of a Tesla, or even much more than that? Well, this is a pretty dumb way to get a strong magnetic field. That's the takeaway. Okay. For one, I can make a stronger magnetic field by not having just a single segment of wire that's running straight. What if I took a wire and wrapped it up into a really, really tight space? Okay, I could create a stronger magnetic field that way. Another thing that could help me is if I use magnetic materials, things like iron and cobalt and nickel. These things enhance the strength of magnetic fields. So yeah, you can actually get a 1 Tesla magnetic field. It's just that this isn't the way you want to do it, because you couldn't possibly run this kind of current through a wire. With that said, we'll end the video here. The next time we come back, we'll go through a lot more examples of Ampere's law and how to use it to calculate a magnetic field. So that'll be next time. Until then, take care. I hope everyone's safe and healthy. See you next time.